Welcome to The Explainer. Today we are unpacking something absolutely fascinating, the engineering of hypertrophy, joint mechanics, and muscle growth. Honestly, if you love figuring out the hidden mechanics of the human body, you are gonna love this. We're completely stripping down the old-school, traditional ideas of building muscle and looking at the whole thing strictly through the lens of physics. It's a massive paradigm shift in how you'll view the gym. So, let's jump right in.
Stop assuming your heaviest sets are actually building the most muscle. In reality, your body's a structural engineering puzzle where joint angles matter more than the weight on the bar. We're dismantling the myth of raw effort to show you how peak torque, not sweat, triggers cellular microtrauma. Okay, let's dive into this because, wow, that directly challenges the ego, doesn't it? I mean, we've all been culturally conditioned by decades of fitness magazines to believe that agonizing, heavy lifting is the absolute gold standard for growth. We've all seen that guy in the gym grunting through a max squat. But this source material forces us to confront that heavy lifting myth head on. It's kind of crazy to realize our perception of effort might be completely flawed.
So we've got this stark contrast between what we're taught and how the body actually works. On one side, there's the myth, raw effort, sweat, and just moving heavy weight. The whole add another plate, grip it harder, yell through the pain mentality. But the reality? Well, reality is rooted in physics, joint angles, and peak torque. Think about it. Your muscle fibers literally do not have eyes. They have no idea if there are two 45-pound plates on the bar or if you're just using a resistance band. What they actually know, what they physically sense, is mechanical tension, and that tension is governed entirely by physics. We're stepping away from that romanticized idea of just sweating it out and moving toward a highly calculated, engineered approach to triggering growth.
To really grasp this, I want you to picture your last really heavy set at the gym. Maybe it was a squat, a bench press, or a heavy barbell curl. Remember how the bar felt, how your muscles were just burning, how hard you pushed. Now, completely erase the concepts of flesh and bone from that memory. Instead, reframe your body in that exact moment as a complex structural engineering system. You are, essentially, a biological machine trying to solve a physics equation. When you approach your training as a structural engineering puzzle, the question suddenly stops being, how do I move this heavy weight from point A to point B? Actually, scratch that. It becomes, how do I manipulate this weight to place the absolute maximum physical stress on the specific structural beam, my muscle, that I want to reinforce?
Let's zoom into the mechanics of that system for a second. Your skeleton is this highly sophisticated lever machinery. Think of your bones as rigid steel beams and your joints, like your elbows, knees, and shoulders, as the pivots or hinges. If an engineer is building a crane, they don't just guess how much weight the crane can lift, right? They calculate the leverage based on the length of the crane's arm and the pivot point. Well, your body works the exact same way. The muscle acts just like a cable pulling on a rigid bone to rotate it around a joint. Once you visualize your anatomy as this interconnected system of rigid beams and pivots, it completely changes everything. You realize that building muscle is quite literally applying targeted mechanical engineering to a biological structure.
Now, what's really interesting about this slide is the most important rule of this entire framework. The sheer weight on the bar is actually secondary to the physical distance between the load and your joints. The distance between the load and the joint axis is what determines your actual force requirements. So, picture holding a 20-pound dumbbell. If you hold it straight down by your side, it feels pretty light, right? Your joint isn't under much rotational stress. But if you hold that exact same 20-pound dumbbell straight out in front of you, with your arm fully locked out, suddenly, no way, it feels incredibly heavy. Your shoulder's probably screaming. Did the dumbbell magically gain weight? No. The load stayed exactly the same, but the distance between the load and your shoulder joint, the pivot, increased dramatically. So the physical force required by your muscles skyrocketed.
That fluctuating distance you feel with the dumbbell? In biomechanics, that is called an internal moment arm. Basically, these are the fluctuating distances between the load and the joint axis that create varying levels of mechanical demand throughout a lift. What this means in plain English, so we don't get lost in the weeds here, is that the mechanical demand on your muscles isn't static. It is constantly changing mid-lift. Think about a bicep curl. The weight feels easy at the very bottom, insanely difficult right in the middle when your forearm is parallel to the floor, and then easy again at the top. Well, that midpoint is where the internal moment arm is at its absolute longest. That is where the demand on your bicep is maxed out, totally regardless of what the dumbbell actually weighs. You're experiencing fluctuating leverage in real time.
So let's see how this builds and actually triggers growth. It happens in a really precise sequence. As you move the weight and those internal moment arms fluctuate, your body eventually hits a point of peak torque.
That is your sticking point, the hardest part of the lift. The moment of maximum mechanical tension where the distance and the load create the ultimate challenge for the muscle. And it is precisely at that moment of maximum tension that cellular microtrauma is triggered. We are zooming all the way down to the cellular level here. That microtrauma, those tiny microscopic tears in the muscle fiber, that is the required stimulus for rapid growth. Your body repairs those tiny tears and builds the muscle back thicker and stronger. It's literally a precision strike engineered by physics. So, the crucial point is this: physics, not effort, is the primary driver of rapid muscular hypertrophy. This distills everything down to one elegant truth. Effort is important, for sure. You obviously still have to show up and you still have to execute the movement. But optimizing your joint mechanics, finding those perfect angles that maximize internal moment arms to hit peak torque, that is where the magic happens. It's an incredibly empowering realization. It's all about training smarter and utilizing the laws of physics to guarantee the biological response you want, instead of just burning yourself out on raw, uncalculated effort.
Which leaves us with this final, incredibly provocative question. At your next gym session, will you lift like a weightlifter, or will you train like an engineer? Are you going to just focus on moving a hunk of iron from point A to point B just to say you did it? Or will you focus on angles, leverage, and torque to systematically construct the physique you want? The tools are exactly the same, but the mindset shift changes the whole shebang. Next time you grab a weight, remember the rigid beams, remember the pivot points, and chase that perfect peak torque. Thank you so much for joining me for this explainer. I hope this completely revolutionizes the way you approach your training. Keep questioning, keep analyzing, and I'll see you in the next one.